Okay, this is volume, and this video is going to really just concentrate on the disk method. And when I say disks, what we're doing here is we're going to take an area. This first area is the curve y equals x to the fourth. So there's this line, and then we're going to cut it off at x equals to 4. Okay, and then we're going to take that area and we're going to rotate it about an axis. So what happens here is you're going to take this area, whip it around the x-axis, and hopefully you can understand that what you get is a cone. So here's our cone. What we want to do is we want to find the volume of that cone. Okay, I'm not really good at drawing any of these, so if you want a better picture of any of these objects, you should just go to the internet and Google, Google image, volume using disks and throw in calculus or something, and I'm sure a ton will pop up. But if you take this and you rotate it this way, what you're going to do is you're going to get a shape that is a cone. And each one of these, so if you take this little one right here, this area, this small thing, and you whip it around, right? Think about whipping that around. You're going to get a little circle there. You're going to get all these circles, but they're not really circles. They're disks because they have a thickness. Okay? And so what would then be the volume? Well, the volume in the disk method, it's always the same. You're integrating, which means you're summing up all of the individual cylindrical disks. Okay? Well, each one of these disks, right? Each one of these disks has this little bitty thickness. That's about as best as I can do. You slap each one of these, and they're all different areas, but they all have thickness dx, but then they have cross-sectional area of pi r squared. And in this case, in most of the cases, you're going to use dx. dx is the thickness. Pi r squared is the cross-sectional area, right? If we shade one of those in, right, that entire area is just pi r squared. And what is r? Well, r is just the function height. And so what we're going to do for this guy is we're just going to say that the volume of this cone is the integral. And again, we're using this formula for every single one of these in this video, from pi x over 4 squared dx. And we're going to sum those up from 0 to 4. All right, so just think about this for a second. We're going to find what happens is you're going to take this area and you're going to rotate it about an axis. In this case, we're rotating about the x-axis, and that's going to form a three-dimensional shape. The shape here is a cone. The cone's volume is the summation of all these cylindrical disks. Each disk has a cross-sectional area of pi r squared and a thickness of dx. And so this then is the individual volume of all the disks, and you're summing them up. We're going to sum up from 0 to 4 because that's the bounds I've chosen. Okay, and when you do this, all of these can be done analytically, meaning you can actually just multiply this out, do the integral, and plug in. I'm going to save some time in the video. If you want to practice, feel free. But you are going to get 4/3 pi as your answer here. Okay, and you can go throw back to a cone. We know that a cone is 1/3 pi r squared h. That's the geometry formula for a cone. And so if you bust that out, 1/3 pi, the radius of my cone would be this distance, which would just be 1. And the height of my cone is this distance, which is 4. Oops, 1 squared, not that that matters. 4, and you get the exact same thing. So the geometry formula 1/3 pi r squared h does agree with the summation of all the disks. Okay, and we're just going to keep working with that, but all of these use this same idea. All right, pi r squared dx, and then later on I'll show you some dy stuff. Okay, so let's look at this one. Let's take the curve y equals x squared. Let's cut it off at x equals to 2. Okay, this is x equals to 2, and we'll revolve this. And for me, this kind of looks like a tornado. Okay, what you have here is you're going to get down, get this guy, and we get all of these disks that we're going to sum up. It kind of looks like a tornado to me. And the procedure is the same. The volume is the summation from 0 to 2, right? Add up all these disks of pi, and r in this case, again, just look at this disk right here. What is its r? It's this distance. That's the radius of this disk. Well, that's just the function curve. That's just that. R squared dx. Don't forget both squared. X squared is because that's the r, and then squaring it, well, because it's pi r squared for the cross-sectional area. And when you do this, you're going to get an answer of 32 fifths pi. Okay, is the volume. Okay, down here, all right, let's take the curve sine x and rotate it about the x-axis. Okay, and you'd get some walnut. All right, kind of looks like a walnut here. And again, you're taking these. You're going to take all of those disks. They each have their own little volume. Integrate. In this case, from 0 to pi. Why pi? Well, because that's this intersection. All right, that's pi comma 0. Go from 0 to pi of pi r. R is the curve, sine x squared dx. This one's a pretty tricky integral to do by hand. Not that you can't. You'd have to know the trig identity that sine squared is equal to 1/2 minus 1/2 cosine 2x and then integrate it from there. But when you plug this out, you do end up getting pi squared over to 2 if you do it analytically. In your calculator, it's probably something like, that's close to 10 divided by 2, so you get something like 5. Okay? All right, let's take this curve. Now remember, this is a semicircle. So this was supposed to be a perfect circle. What do you expect to get if you take a circle and you revolve it around its diameter, or well, it's not really diameter, but I guess it's just the x-axis in this case? Well, you better get a sphere. And again, if you draw this, it's not going to be perfect because I can't really do it very well, but just imagine that that's a three-dimensional shape of it and it's whipped around. Well, that's going to be a sphere. It's still going to be the same thing. The volume, again, you might not think of a sphere, but you can take a sphere, and if you get enough of these disks perfectly, and you stack them, well, you get a basketball. Okay, so this is just a ball. And the volume is the integral, in this case from -2 to 2. And again, I know that because the radius of the sphere is 2. The radius of the circle is 2, which is the radius of the sphere. Okay, and we're going to get pi r, which is just the function 4 minus x squared, which is nice because the square and the square root kind of go away, and then dx. And when you do this, you get 32 thirds pi. Okay, and we can verify this. The volume of a sphere is 4/3 pi r cubed. And check it out. If you use a radius of 2, which is what our sphere would have, 2 cubed is 8, 8 times 4 is 32, and boom, they match. Again, the calculus matches the geometry. Okay, let's do this one. Let's not take this whole curve, because then we just get a cone again. Let's start at x equals to 1, and go to x equals to 2. So let's only take this area and whip it around the x-axis. Well, if you do that, you get this kind of lampshade. Okay, you get this lampshade kind of picture. So it's going to look like something like that. And again, that's the best I can do. I think it kind of looks like a lampshade. Kind of on the side, of course, but it's a lampshade. So we find the volume in the same way. The volume is just summing up. In this case, we're only going to go from 1 to 2. Pi r, well, this is still the r, right? This distance, right? This is the center line. This distance is still just the curve, so it's just 2x squared dx. And when you get this, you're going to get 28 thirds pi. You can verify that with geometry because the lampshade, this part, is really just this big cone minus this little cone's volume, and you can show that it's the same thing. All right, new one. So if you fell asleep when I was doing all these with x, now I'm going to do one with y. Let's take x squared bounded at the top by y equals to 4. Right, so this means this intersection, right, is 2 comma 4. And let's revolve it around the y-axis. So we're going to get something that looks like this. Okay. Okay, let's call this the grapefruit. All right, good grapefruit for breakfast. Slice it in half, and then you get something like this. Okay, so now we're going to still sum them up, but instead of summing with x's, we're going to sum to y. So instead of going 0 to 2, we're going to go 0 to 4. Just look at it. Look at these, the discs here. They have thickness dy. So we need to sum them up. So we're stacking them from 0 to 4 of pi, and then r. Well, r is this distance. Remember, if y equals x squared, that's the same thing that says x equals the square root of y. So this distance, the square root of y, is our r. Square root of y squared and dy. Y limits, y stuff, in your integrand, or your pi r. Your r is a function of y, and then dy. They'll always match. X limits, x's, dx. Y limits, y, dy. Always going to be true. You're never going to have an x here and a dy here. You're never going to have y here and have x limits. Just doesn't really make any sense, right? You're summing up, you're stacking the discs vertically, so it makes sense to use y. Okay, and when you do that, you get 8 pi. Okay, those are my first 6 examples. All of these, I took different curves and I revolved them around an axis. However, it doesn't have to be just around the x-axis and y-axis. So what does it mean for a disc to work? Okay, so I want to prove to you that I don't have to just go around y and x to have a disc. Let's use the curve y equals x squared and x equals to 2, and let's revolve it around x equals to 2. And this is still a disc problem. So how do you know when you're going to use discs? Well, you might not even know any other methods yet. You might not have seen washers or cylindrical shells yet, but in the future, you're going to have to pick out which method to use. Discs are always when you're rotating an area around an adjacent axis, meaning the area you rotate around is completely adjacent, totally touching, no gap between your area and the axis. So discs I could do here, I could do here. But if I did this axis, you can't use discs anymore. It's going to have a monster hole here. So let's just go with here, and then we'll do washers in the next video. But let's revolve around this line. And so what you're going to have here is something that looks like this, right? You have like a tornado that's flipped upside down, right? So the tornado is usually the ground is here in the air, so now it's flipped this way, or this is some mountain of sand, or this parabolic kind of pyramid looking shape, whatever you want to make it out to be. But is it x or is it y? Think about it for a second. Look at each of these cylindrical discs. How are you stacking them? You're stacking them vertically, so you know you have to be in terms of y. So you're going to stack them, and again, if this is x equals to 2, this is the point 2 comma 4. So the volume is going to stack these things from 0 to 4, y values, pi, and then r. This one's a little trickier. Just look at one of these discs and label that distance is your r value for that particular disc. Well, what is that distance? Well, this distance is the square root of y. This whole distance is 2. So then r is going to be 2 minus the square root of y squared and dy. Again, take some time and think about how am I going to find this distance. From here to here is 2. From here to here is the square root of y. It's x. And I need this. I need the difference between this. And so it kind of goes back to our area. It's just right curve minus left curve. Right curve minus left curve gives you this particular distance. And again, all we're doing is summing up cylindrical discs. Each disc is pi r squared, in this case dy. And when you sum those up, I believe you get 8/3. And again, if any of my numbers happen to be wrong, then don't be too mad at me. But all the problems are certainly set up right. And you can tell me in class later if I screwed up one of the actual numbers. Okay, let's do this one now. Same thing. This is a nice easy line. Let's bound it by y equals to 2. Remind you that this then is the point 6 comma 2. Then let's revolve it not around the y-axis. Let's revolve it around the line y equals to 2. So what you're going to get here is a cone. We're going to find the volume of the cone by stacking them. And again, look at the thickness. The thickness of each disk is dx. So you know we're with x's. So we're going to sum up from 0 to 6, right? Use the x value, pi, and then what's r? Again, just look at this particular disk right there. This is its r value. What's that distance? Well, from here to here is 2. From here to here is x over 3. So it's just the top curve. 2 minus x over 3 squared is your r. Pi r squared dx in this case. Sum all that up that bad boy and get 8 pi. Okay, so I kind of tried to take you all through all the scenarios of all the different volumes of these things using discs. Here's the first one again. We can get all these different shapes. The key for discs is that we always use this formula, and we can use this formula, and if you look here, there's no holes. All of these are solid objects. Cone, tornado, walnut, ball, grapefruit, there's no hole in them. There's no hole because the area I was revolving is completely adjacent to the axis of revolution or rotation. Okay, that's discs. You can look for a couple future videos when I'll do washers and I'll do cylindrical shells, which kind of are the advanced versions of when things are shifted.